Thank you, organizers, for this opportunity. I want to talk about index distribution for short-range Riesz gas. And this work is done with Manas, Anupam, Satya, David, and Gregory. So what do I mean by index distribution? Basically, consider you have a wall on a line, and there are multiple particles on the left of the wall, and there are some particles on the right of it. These particles could be non-interacting or interacting. But from configuration to configuration, the number of particles on the left and the number of particles on the right would be different. So what I'm interested in understanding is what is the distribution of particles on the left of this wall. When they are non-interacting, it's natural to understand this distribution is going to be Gaussian because these are independent particles. Central limit theorem, there are n particles. The variance should be proportional to n, it's Gaussian. But when you have interaction, what happens? That's what we want to understand. This distribution problem is actually part of a broader class of problem called full counting statistics, which measures the number of particles in any designated domain. And it's actually a useful quantity to understand physical equilibrium and non-equilibrium properties. For example, entanglement entropy for the free Fermi gas can be connected to the full counting statistics. And it's since it's a global observable in a sense that you don't have to keep track of each particle. You can just look at the cloud, and just looking at the cloud and the variance of number of particles, you can comment something about the nature of the interaction between the particles. In classical context, in a sense that for some systems you can use full counting statistics, especially the variance, to understand whether the system is hyper-uniform or not. By hyper-uniform, you mean it's extremely rigid and the fluctuations are suppressed. But even though this is actually an interesting problem, the analytical understanding is limited. The reason for that is the calculations are different. If you have interaction, it becomes difficult. However, there are some cases where some cases like Dyson's log gas, where the particles repel each other with a logarithmic interaction, and one component plasma, that is like 1D Coulomb gas, that repel like a interaction energy is linear in the distance between the particle. For this system, we understand the full counting statistics, but we want to understand what we did here is to analytically try to understand a a different class of model, which is basically a power law model, power law model, and all the particles interact with all remaining particles, and this power law, since it's interacting with all the particles, is effectively long range. However, because the exponent is greater than 1 and we are considering a system in 1 dimension, this interaction itself is short range. However, the model is part of a long range model. What we notice is we confine these particles to a harmonic trap. Basically, this will not allow the particles to fly away. And since this is repelling system, it could fly away, but this actually holds them down. And because of that, there is a length scale, a typical length scale where the particles cannot go, they stay in the length scale which is of the order n to the power alpha k, and alpha k depends on which interaction you're choosing. And because of this length scale, turns out the energy is super extensive. For normal system, we know that energy, if you have n particles, energy and make double the number of particles, energy becomes double. However, this is super extensive in a sense that energy becomes more than double. Now that we understand some aspects of Riesz gas, I'll point out one more property of Riesz gas, which is that for the short range Riesz gas, the energy is actually local in density. If you Gauss crane the energy, it's local in density. And this is a very useful, this is basically the key to solving the index problem. Using this local energy, people were able to compute the equilibrium density profile at order 1 temperatures. So note that energy is actually super extensive, and entropy is generally extensive. It has to be extensive because it's a counting problem. So at order 1 temperature, it is energy which determines the behavior of the gas. And turns out that the particles in the equilibrium, the ground state, because we are talking about low temperature, entropy is not important, it's effectively like a 0 temperature state. There, the state is actually bounded between minus L0 and L0. Basically, it has a finite support. It does not have smooth tails generally expected out of temperature. Systems with some temperature and confinement. Now that we understand this, we compute the index distribution, which is basically the probability distribution of number of particles in the domain -infinity to W when the system is in Gibbs equilibrium. By Gibbs equilibrium, I mean that the system has some temperature, and any configuration, if I choose a random configuration of particles, position of the particles, it will be distributed with this probability. Now I want to understand, let's say there were m particles instead of all particles, there were m particles in this region. There could be configurations where the mth particle is, let's say, at infinity. However, there could be configuration where all the particles are concentrated here. So we have to add all the probabilities, and turns out the index distribution is actually dominated by the probability, which corresponds to a minimum energy configuration when there are m particles here and remaining particles here. So we have to, it's an optimization problem at the end of the day. Optimization that there are m particles, remaining particles are here, and such a configuration is what we are looking for. This could be made more formal from Coulomb gas method, where you basically measure you add all the configurations, the probability of all the configurations with Cn particles on the left of W. And since energy is super extensive, this will be dominated by the minimum energy configuration, and that's what we do. We want to extremize this action. Extremization gives us a saddle point equation. Solving the saddle point equation, we get densities. Density, because we have to do everything in densities, it's easier. So we get the saddle point densities, and using the saddle point density, we can compute the probability distribution, because it's just going to be a last deviation form, where the last deviation function is the extra energy required to create such a configuration. This is the ground state energy, and this is the energy of the new state. Let's look at how the density profiles look like. We note that depending on the fraction of particles to the left of W and where the wall is, we could find three different kinds of density profile. When, let's say, there were no particles, obviously no particles on the left of W, you'll only find this dome. This dome, you won't find this density. However, when you do for, let's say, there are some finite amount of particles on the left of W, you'll find that there is a droplet which is forming at the bottom of the harmonic trap. And if you keep adding, removing particles from here and keep adding, you'll find that that droplet actually expands. And if it expands, it can expand till, okay, from going from here to here, you'll find that this droplet is expanding at exactly C bar equals to W, C equals to C bar, you find this droplet touches the wall. And if you go further than that, if you add even more particle, you'll find that since it cannot expand further, the density at this point will increase. And if you keep adding more particle, at this point you'll find that the density at exactly this point, you would have observed this black line. However, because the concentration is more, you observe more density here. This three different shape actually lead to some interesting behavior, which I'll just describe in a moment. But before we describe that, let's look at the last deviation function. How does it look? So last deviation function is basically the extra energy required to create such a configuration, and that extra energy is nothing but energy of the left portion plus energy of the right portion. Why? Because the system is, the energy is local in nature. That's why it turns out, and we have some analytical expression for this, which I'm not showing. However, how does it look like? So we find that if you are, this is C versus W. Yeah, when you are at some fraction of particle and you are pushing the particle, let's say wall is at origin, and you're pushing the wall further and further from the origin, what you find is initially there is a decrease in requirement of energy and then again an increase. And at this point, this is the point where you actually are talking about the equilibrium. Beyond this, ground state, and beyond this you are actually away from ground state. And this is the point where this whole region is formed. This actually leads to a phase transition, which I'll describe. This is no phase transition, it's just Gaussian kind of behavior here. Similarly, when you fix the wall position and start adding more particles to the left of it, you get similar behavior. But before we jump into the phase transition, what we find is, for non-interacting system, we found that number of particles are distributed as a Gaussian. Here also we find that it's Gaussian. However, the variance does not scales with system size as n to the power nu k, not n, like just n. And this nu k depends on 2 minus k by 2 plus k. Nu k is basically 2 minus k by 2 plus k. What it means is when the interaction is between 1 and 2, this is diverging. The variance is increasing with system size. When k is greater than 2, variance is decreasing with system size. What does it mean to decrease with system size? It means that the system has become rigid completely. And we actually are able to verify this numerically using Monte Carlo simulations. We see that variance matches the theory matches the simulations. Now that we understand how the the large deviation behave at the C star, we want to understand how the large deviation function behaves at this point when we are trying to cross this line. We find that the first derivative, which is red, second is green, and third derivative is blue. We find that the third derivative has a discontinuity. Here also you note that there is a discontinuity. This effectively says that the system undergoes a third order phase transition. And we can actually analytically compute these things. Okay, and this is one aspect of the work which I have done. But using this idea, we could also compute pressure of the Riesz gas. Basically, pressure for the thermodynamic pressure for the Riesz gas is amount of energy required to push all the particles on the left by some amount, epsilon amount. Let's say work per unit displacement is what the pressure is, and that's what we can compute because we know what is E left energy of the particles on the left. So we can just do the calculation, we get the analytical expression for the pressure. In a similar fashion, we can compute the mechanical pressure. I'll take one more minute. Mechanical pressure is basically basically the momentum current, which effectively means there are particles on the left and there are particles on the right? So how much are these particles pushing all the remaining particles? It's given by this expression. We can compute this numerically. We have this analytical expression. We compare this with Monte Carlo simulation, and we see that pressure is actually matching the mechanical. Thermodynamic pressure is matching the mechanical pressure. In a similar fashion, we can compute the bulk modulus. Bulk modulus is like an effective spring constant of a system. We can compute bulk modulus from linear response, where we can relate the bulk modulus with the second moment of the position of the mth particle, which is basically a fluctuation response kind of relation. And this variance can be computed from index distribution, turns out. Because let's say if there are m particles to the left of W, that means position of the mth particle is exactly at W. That is the CDF of position of the mth particle. And from there we can relate the CDF of mth particle with the large deviation function for the index distribution, and from there we can compute the second moment, because from large deviation function we can compute the variance, which is second derivative, and from there we have the compressibility expression for compressibility. I haven't shown the expression though, and we find that it matches with the Monte Carlo simulations. In summary, basically we have studied index distribution problem. We found that typical fluctuations are Gaussian, and it scales as n to the power nu k, where nu k depends on k. It's not like a non-interacting problem. And the saddle point densities have some interesting shapes, and these shapes actually lead to a phase transition. And also we could compute pressure and bulk modulus because energy is local. Thank you.
How much of it is actually exclusive to also your confining potential, which is harmonic? And if you change your confining potential, what does it change?
The pressure does not change. Pressure, compressibility, of course the expressions changes. Pressure का expression change नहीं होगा, bulk modulus का expression will change. But all these third order phase transition and typical behavior, it's Gaussian, that won't change. But the scaling, it scales as n to the power nu k, right? That nu k will change. We have done this calculation, though I've not just presented.
You had some specific system in mind, but in a more slightly more complicated system, will this help in calculation of currents, like transport coefficients and all of some heat or something?
Yeah, the full counting statistics, when it comes in the context of transport only between T and T
Yeah.
plus dt, how many particles have crossed a certain boundary, let's say. But it's a, yeah, I mean, I'm not working on, this is actually different. I mean, it's related probably, but not
I
directly.
mean, you're really in a thermal system, right now?
Yeah,
It's
the
not
system is
quite
in Gibbs equilibrium,
Yeah,
yes.
it's not quite a non-equilibrium setup.
Yeah,
Even though
it's a
it might be
equilibrium.
useful for this counting statistic might be useful for non-equilibrium counting, as you were
Absolutely.
non-equilibrium calculations, as you were saying earlier.
Yeah. This is completely equilibrium. I have not done any non-equilibrium here.
Any more questions? If there are no more questions, let's thank the speaker.